We're now going to derive the impedance of a capacitor. And again, impedance we have defined as being the ratio of the phasor voltage to the phasor current. So let's determine that relationship now for a capacitor. Once again, we're going to define a voltage or reference voltage V of t and a current flowing through the capacitor flowing or is referenced from the positive to the negative referenced terminal. Now this time around, let's assume that the voltage in the capacitor is equal to, or is of the form V sub m cosine of omega t plus theta sub v. And we know that in a capacitor, I is equal to C times the derivative of the voltage, which is going to equal then C. Now once again, the derivative of the cosine is negative the sine, so we'll bring the negative out in front here. The chain rule is going to give us an omega out in front. We have then the V sub m, and we'll have then the sine. The derivative of the cosine is the sine with the negative already taken care of, sine of omega t plus theta sub v. And once again, we want to write this in terms of a cosine rather than a sine. So this is going to equal negative c times omega times v sub m times the cosine of omega t plus theta sub v minus 90 degrees. Now, let's write both of these in their phasor forms. This time we have phasor v is equal to v sub m e to the j theta sub v. And we can write phasor I is equal to negative c omega v sub m e to the j theta sub v minus 90 degrees. Again, using the product of two exponential terms is equal to, you add the exponents. We're going to undo that. So we have then this is equal to negative c omega v sub m e to the j theta sub v e to the minus j 90 degrees. As before, this term right there is just minus j. So we take the minus times the minus, that gives us a positive, and bringing the j into this mix here, we have then j omega c v sub m e to the j theta sub v. And again, we recognize that right there as being phasor v. So we can then write that I, phasor I, is equal to j omega c times phasor v. Now let's go ahead and form the impedance by writing the ratio of phasor v to phasor I. We have z then is equal to phasor v divided by phasor I, but phasor I is just j omega c times phasor v. The phasor v's cancel, and we get then that the impedance of a capacitor is equal to 1 over j omega c. And sometimes we'll write that by bringing the j up into the numerator, changing the sign on it, which then gives us a negative j times 1 over omega c. Alrighty, and we need to make some observations here. First of all, notice that the impedance of the capacitor is negative. Second of all, notice the frequency dependency of the capacitor impedance is inversely. In other words, to say it better, the impedance of the capacitor is inversely proportional to the frequency of the circuit source that's driving it. Remind ourselves here, the impedance of an inductor was J times omega L. The impedance of an inductor was directly proportional to the frequency. The impedance of the capacitor is inversely proportional to the frequency. When the frequency is small, the impedance of the capacitor is large. And in fact, at DC, when omega equals 0, the capacitor has an infinite impedance. It is effectively an open circuit. As the frequency gets larger and larger, and as the frequency approaches infinity, a larger and larger number in the denominator makes the impedance of the capacitor get smaller and smaller, and in the limit as omega goes to infinity, the impedance of the capacitor goes to 0. At high frequencies, the capacitor is approximated by a short circuit. So for example, Let's say that we've got a 10 microfarad capacitor, and that the source is driving this is some V sub s of t is equal to 5 cosine of 5,000 t. In other words, omega is equal to 5,000 radians per second. Then the impedance of the capacitor in this circuit, this 10 microfarad capacitor, would be equal to 1 over J times omega, which is 5,000, times C, which is 10 times 10 to the minus 6th. You do the math on that, again bringing the J up into the numerator, and you'll get that the impedance of this capacitor would be negative J20. And as we mentioned, the impedance of the capacitor is negative. The impedance of the inductor is positive. The impedance of the inductor, in fact, let's just make a little chart here. In the time domain, R and the impedance for a resistor is just plain old R. For a capacitor, the impedance of a capacitor is 1 over J omega C. And for an inductor, the impedance of the inductor is J omega L. And finally, in each of these cases, Ohm's law applies. We have then that V is equal to I times Z, because we defined Z to be the ratio of phasor V to phasor I.